We will do some more exercises. The first one is called the Saint-Venant problem. So you think of a beam, infinite beam of uniform cross section. So omega is a container with some inclusions. Think of concrete with steel rods stuck inside. So the rods are going through along with this beam, and so this is the cross section of the beam, and these inclusions here denote the places occupied by the cross sections of the steel rods. So this is called, so we want to study what is called the torsional rigidity of this beam, which means how it is, how stiff it is, and so on. So let omega naught contained in R2 be a bounded open connected set. Gamma naught equals d omega naught. Let omega I equals 1 to m be open mutually disjoint subdomains. That means they are also open sets and they are connected themselves. Okay. So gamma I equals d omega I 1 less than equal to I less than equal to m, and we write, let the measure of omega I equals ai 1 less than equal to I less than equal to m, and let omega equals omega naught minus union I equals 1 to m omega I closure. That means you remove, it is the portion which other than the black shaded region. So it is that which is called omega. Okay. So find u such that minus Laplacian u equals 2 in omega, u equal to 0 on gamma naught, u equal to Ci on gamma I, an unknown constant, Ci which is strictly bigger than 0, okay, unknown constant 1 less than equal to I less than equal to m, and integral, since these constants are unknown, you need another condition to fix them. So that is integral du by d nu d sigma I d sigma on gamma I equals twice ai. Okay, so u is called warping function on omega. Okay, so this is the thing, and the torsional rigidity is determined in terms of the gradient of u. Okay, so we want to show that there exists a unique solution. Okay, so solution, step 1, we will unique weak solution or unique solution. Okay. So unique, so step 1, uniqueness. So let u1 u2 be two solutions, and you said w equals u1 minus u2. So minus Laplacian w equal to 0 in omega and w equal to 0 on gamma naught. Okay, so 0 equals integral on omega minus Laplacian w times w dx, and that's equal to integral on omega mod grad w square dx. There is no integral on gamma naught, but there is integral on gamma I. So minus sigma I equals 1 to n integral on gamma I w dw by d nu d sigma. Okay. So, now this is equal to integral on omega mod grad w square dx, okay, minus sigma I m. I equals 1 to m, okay. So, you have C 1I minus C 2I integral on gamma I du 1 by d nu minus du 2 by d nu d sigma, because the w is equal to a constant, u1 and u2 are equal to constants on the gamma I, and then you have du1. But then this is equal to 0 because du1 by d nu equals integral du2 by d nu, each is equal to 2 times ai, that is the last condition here, and therefore you have that this is equal to 0. So, this means that grad w equal to 0 and w equal to 0 on gamma naught. So, Poincare holds implies that w is equal to 0. Okay. So, you have u1 equal to u2. So, now we want to show the existence of a solution. Step 2. So, let C equal to C1 Cm belong to Rm. So, you define u of C equal to V solution of minus Laplacian V equal to 2 in omega, V equal to 0 on gamma naught, V equal to Ci on gamma I, 1 less than equal to I less than equal to. So, this is a straightforward Dirichlet problem and everything is fine, therefore, there exists unique V. And let W in H1 0 of omega such that minus Laplacian W equal to 2 in omega and W equal to 0 on d omega. This also exists, there exists unique W. So, this also is fine. So, now you define beta I equals integral on gamma I dw by d nu d sigma and di equal to integral dv by d nu over gamma I d sigma 1 less than equal to I less than equal to m. Okay. So, d equals d1 dm in Rm. So, now if you take lambda which maps C to D is linear Rm to Rm. So, we want to know if it is invertible. Okay. So, assume lambda of C equal to 0. That means 0 equals integral minus delta V on omega, this should be 0 here, equal to integral on omega mod grad V square dx minus sigma I equals 1 to n m of Ci integral gamma I dv by d nu I. But this is equal to di and that is equal to lambda of C I, and therefore that is equal to 0, that is given to you. And therefore, again this implies since V is also 0 on gamma naught, you have, so V is 0 on gamma naught. So, Poincare holds and therefore, this implies that V equal to 0 and this implies that C equal to 0 because C is nothing, Ci is nothing but dvi integral dvi by Ci is, so everything is 0, minus Laplacian V equals 0, V equals 0 on gamma naught, V equals 0 on gamma I, so V is 0 and V equal to Ci on gamma I, and therefore that means Ci is 0 or C equal to 0. So lambda is 1 1 implies on 2 and invertible. So given D in Rm, there exists unique C in Rm such that lambda C equal to D. Now you define T of C equals lambda C plus beta. So beta equals beta 1 to beta m. Okay. Now if you take Di equal to 2ai minus beta I, then this will imply that Tc is nothing but 2ai. So now if you set u equal to u of c, which is equal to v of course, plus w, then you have minus Laplacian w equal to 2 in omega, because uc minus Laplacian w is 0 and for this one it is 2, so when you add them you will get 2, w equals 0 on gamma naught and w equal to Ci on gamma I, and integral dw by d nu on gamma I, this is nothing but di, which is equal to 2ai. Sorry, dw by d nu plus dv by d nu, this is equal to, oops, u. So integral gamma du by d nu d sigma equal to integral dw by d nu, which is equal to beta I plus lambda of c, and that is equal to Tc equals 2ai. Okay, so this is also, so you have it satisfies all these conditions, 1 less than or equal to I less than or equal to m. But we still have to check. So step 3, claim Ci is positive. Okay, that was also one of the conditions in the original problem, Ci which is positive. Okay, so we have to check that, and therefore we have to claim that Ci is positive, 1 less than or equal to I less than or equal to. So up to now, given any constant integral du by d nu equals anything, you can always solve the problem. But Ci we have no control, but by putting it equal to 2 of 2ai, we can even claim that Ci has to be positive, and that is and it's also, I'll give it in the assignment, it will be you can have a good weak formulation because of that. Okay, so let omega be smooth enough. Okay, so this implies that u is in H2 of omega, and that since will be in C of omega bar, since we are omega is contained in R2 by the Sobolev embedding theorem. Okay, so then if you take x naught in omega bar, then such that u of x naught equals minimum of u of x in omega bar. Okay, so suppose x naught is in omega. Okay, this implies that grad u x naught equal to 0, and Laplacian u, the second derivatives at x naught, must be greater than or equal to 0, but that is not possible since Laplacian u is equal to minus 2. Okay, so that is not possible. So, let x naught belong to some gamma I. Okay. Then you have, this implies that minimum of u is in fact Ci. But then if you have, so this is a variation, so this is gamma I. So, Ci is the minimum of u, that means if you approach it along the normal direction here, it is a decreasing function. So, this means that integral du by d nu is less than 0 on gamma I, but integral du by d nu on gamma I d sigma equals 2 ai, which is strictly positive. So, again that is not possible. So, this implies that x naught must belong to gamma naught, and that means only and nowhere else. So, this means u of x is strictly positive in omega closure minus gamma naught, and this implies that Ci are all strictly positive. Okay, so this proves, so smoothness needed only in last step. Okay. So, the torsional rigidity is defined as integral s of omega equals definition integral mod grad u square on omega dx. This is called the torsional rigidity. Okay.